when you take a look at a heating curve, guys, or a cooling curve, you can see that there are kind of different sections, different parts to the curve. All right, there's slope lines, and there are flat lines on the curves. Nothing's up there? All right, no, just the laser pointer right now. So guys, you've got the slope lines, you've got the flat lines. Obviously, there's going to be similarities in each of those sections. It's your job and your task to know what's going on in each of those sections. So what I want you to do is we're going to draw lines to separate those sections. They do not have to be straight. All right, do your best. Don't worry about getting a ruler out. All right. So we've got 5 different sections, and it is your task to know what's going on in there. Highlighter might be a good tool to have, all right, to kind of coordinate them so it's a little bit easier to see. I'm going to be using different colors in each section. That's up to you. So when we take a look at this graph, first off, it's called a heating curve. Endothermic. What does that term endothermic mean? Gaining, right? So guys, endo means to gain or to increase. Thermic implies heat. Another term for heat is also what? Thermo means heat, but there's another way we measure heat, guys. This means the same thing. It is energy. Energy and heat are interchangeable. All right, so endothermic means gaining / absorbing heat or energy. Okay? You're gaining / absorbing heat and energy. Heat and energy mean the same thing. Gaining and absorbing, obviously. So there's different key words that you're going to see within a problem. So overall here, with a heating curve, an endothermic one, what's happening with our temperature overall? It's an overall increase. Now there's different pieces to our line where there's kind of flat lines and then there's slope lines. And we'll talk about what those mean and what those imply here in a few minutes. Right? But overall, we're gaining heat and energy as time goes by. Right? Temperature is always increasing. So we got to think about this. There are, within these heating curves and cooling curves, they represent and show our states of matter. All right? What are our 3 states of matter that we're interested in this class? Solid, liquid, and gas. Based on what you guys know about temperature and what you know about the states of matter, let's start over there to the left, that first section. Why do you say solid, Sam? Right. There's less heat and energy, guys, and that's what's taking place. Your hands, if we put them together, they're not moving as much. They're staying in place. They're vibrating because they have the least amount of energy. So that cooler temperature is how you know that it is a solid state. All right, so here we've got the solid state. All right, so we've got our solid state. Now, what are we doing to that solid in this section? We're heating it. Is it possible to heat a substance without undergoing a phase change?
No. Yes.
So here, yes and no. Think about this. I'm sure all of you guys have done this before. Boiled water. What do you use to boil water?
Heat.
Obviously heat, but you don't just put water on heat, right? You have a pot. What are you doing to the pot? You're heating it. Does it start to melt the pot when you heat it on the stove? No, guys, because metal has a high melting point, but you can still heat it up. You don't want to touch the pot. It's going to hurt. All right? So, in this section, we are heating our solid. Now, it seems obvious when I say that, but when I ask questions, what's happening during this phase or this part from this line to this line, people don't realize, that you can heat something. You can heat the phases without changing their states of matter. So in this section, there's 3 things we've got to describe: temperature, kinetic energy, and potential energy. What's happening to the temperature? It should be easy. It's increasing. Now, temperature directly measures what? Kinetic energy, guys. It's one of our 5 points of KMT, is that average kinetic energy equals temperature. So if temperature increases, what happens to the kinetic energy? Bless you. It increases as well. Now, kinetic energy means movement. Potential energy means what? Kind of stationary, right? It's that ability to do something, but you're not actually doing it. You're storing up energy. So if kinetic energy is increasing, what's going to happen to the potential energy? It's not going to decrease. It's going to stay the same. It's going to remain constant. Guys, if I draw a straight line across, do we understand that that means constant? If not, jot it down in your on your foldable so that you know what it is, but that's how I'm going to indicate constant. So all of that information is taking place in that one subsection of our overall graph. All right? We're heating the solid, temperature and kinetic energy are increasing, potential energy is staying the same. All right? As we continue along on our graph, if we look at the next section, what's different about this line? It's straight, right? It's horizontal. Does it have a slope? No. All right, so here we have a flat line. A flat line, guys, equals a phase change. Yes, I spelled flat incorrectly. All right, I get that. But there's a purpose behind it. Flat phase, folks. Flat line equals a phase change. So yeah, it's silly and stupid. I get it, why I wrote flat like that. But I'm telling you, for a couple of you, that's how you're going to remember that this is a phase change. All right? Anything, I don't care how stupid it seems, but for some of you, if even one person remembers it, I know that's why I did it. All right? I don't care. All right? Laugh all you want. Flat line equals a phase change. All right? No. Of course I know how to spell flat. All right, well, I know, but I got to keep you on your toes, right? So a flat line, guys, equals a phase change. What phase change is occurring? What state of matter are we starting at in this section? Solid. And we're going to a what? To a liquid. Solid to liquid is known as what? Melting. All right, so guys, we have melting occurring as we go from left to right. Melting is occurring. So we've got to describe our three pieces like we did with the solid state. Temperature, kinetic energy, and potential energy. What's happening with my temperature here? It's staying constant because it's that flat line. Kinetic energy is also staying constant. What's happening to our potential energy? It's going to increase, right? Because again, this is an endothermic graph, so your energy is constantly always being absorbed. All right, so potential energy is going to increase. It's not doing anything, but it's building up that energy that will allow the particles to then break apart and move further apart to be able to move more in our next section. All right? So our next one, we go from solid, then we undergo a phase change. We're going from solid to liquid. What's our next piece? What state of matter do I have? Liquid. All right, so there's my liquid state of matter. Guys, you can write with a capital L if you want. I tend to write liquid with a lowercase cursive L. All right, like it's shown right there. That's okay. Whatever floats your boat. What are we doing to the liquid in this section? No, we're not. We're heating it. We're heating the liquid. All right, we're heating it up. So what's happening to our temperature? It's rising. Kinetic energy is rising as well, and potential energy is staying constant. Hopefully, guys, you start to see a pattern form, all right, within our sections. Now, the next section, again, what type of line is it? It's a flat line, which equals a phase change. Flat line equals a phase change. All right, we're going from a what to a what here? Liquid to a gas, which is known as what? Boiling. Another term is? No, it's not evaporating. Vaporization. We'll talk about this here in just a second. What's the difference between the two? All right, boiling and vaporization, guys, mean the same thing. Evaporation does not. We'll come back to that in just a second. Okay? Temperature, kinetic energy, and potential energy. What's happening to the temperature? Constant. Kinetic energy is? Potential energy is? Increasing. So, all right, again, you can start to see that pattern form. Now, the last section is going to be what? There's our gas phase. All right, what are we doing to the gas? we're heating the gas. All right. What's happening to our temperature? Kinetic energy. Potential energy. Remaining constant. All right, it's remaining constant. So here's what's going on in each section within our heating curve. Energy is being absorbed throughout the entire thing. And we go from state to state to state, undergoing phase changes, and that's what happens with our temperature and kinetic energy. Now, let's go back, guys, to this term right here, vaporization and boiling. All right, because people said evaporation. All right, there's a difference between the two. They are all going from that liquid to gas state. All right, they're all describing a phase change. But it's how that change is occurring that's different. Caroline? What's that? Yeah, what's that? What do you think evaporation is?
Liquid turns into gas without reaching its boiling point.
Yep.
Say water and sunlight, the water evaporates because of the sun and energy from the sun.
Absolutely, guys. So evaporation is occurring when you're going from that liquid to gas phase, but it's not at the boiling point. Okay? What's happening is you have the particles escaping from the liquid to the gas phase, but only at the surface. I would highly recommend jotting this down somewhere in your foldable, wherever you have space, or at least writing it down in your note packet. You can put it at the bottom where it says heating and cooling curves, or on the very back. If you flip to the very back of your foldable where we were yesterday, where it looked like this, all right, I'll jot it down here. All right, wherever you have space. Evaporation. All right, it's liquid to gas, but not at the boiling point. Okay? It occurs only at the surface of your substance. All right? Evaporation is liquid to gas, but not at the boiling point. It's only at the surface of your substance. Whereas boiling or vaporization this would then be liquid to gas at the boiling point. Okay? And it's all throughout. Okay? It's all throughout the substance. That's a huge difference. Evaporation, guys, is happening all the time. All right? If you leave a glass of water out overnight, it's going to eventually evaporate. Now, it may not evaporate overnight. All right? It may take a few days, but eventually all those particles will escape from the liquid to gas state without adding any extra energy to it. All right? Boiling, however, you have to add energy. You have to raise the temperature of the entire substance to get it to go. Think about when you boil water. Where do you see the bubbles first? Really? At the bottom. They start at the bottom, all right? And then when it starts to go on a raging boil, it boils all throughout the substance. Guys, evaporation does not occur all throughout your substance. You don't see bubbles at the bottom. Now, bubbles can form, but they're not escaping to that gas phase right there at the bottom like it is with boiling. That's the difference. You have to know the difference. You're going to be asked about it next week on your test, all right? Even on your final exam, there's a good chance you could see a question like asking the difference between the two. All right, so make sure you know the difference between boiling / vaporization and then evaporation. They don't mean the same thing. Questions about this heating curve? What I want you guys to do right now in your foldable is to go to the cooling curve, which is at the top of your page. All right here. I want you to go through, break it up into the 5 sections, and do your best to start labeling and describing what's happening in each section. All right, so what automatically? So already, guys, what do you notice? First off, exothermic is that new term. What does exothermic mean? Right, we're releasing heat / energy. Okay, so the overall idea here is that we are decreasing or releasing that energy as we go from left to right. Okay? So, what do we start out at here? We start with the gas phase, right? Because we're at the highest temperature, so it should make sense that we are at the gas phase. What are we doing to the gas? Right, we're cooling the gas. All right. Then what's happening with the temperature? Kinetic energy, potential energy. All right, remaining constant. Moving on to the next section. All right, what do we have going on here? Yeah, we get that flat line equals a phase change. What phase change? We're going from a gas to a, which is known as condensation. Okay, so temperature is constant, kinetic energy is, potential energy is decreasing, right? Since we're removing energy from the system the entire time, potential energy now is going to decrease. Then we move into our next section, which is the what? Liquid. What are we doing to the liquid? We're cooling our liquid. All right, temperature is, kinetic energy is, and potential energy is remaining constant. Roll in again to the phase change. Going from a liquid to a, now what is this called? All right, so there's a few different terms, guys, that you can use here. This is known as freezing, or solidification, or there's another term that starts with an F as well, fusion. All right, all of those three terms mean the same thing. It means you're dealing with that phase change from the liquid to solid state. They're coming together. All right, the particles are coming together. Temperature is, kinetic energy is, potential energy is decreasing. And then our last state here is going to be obviously the, what are we doing to the solid? Temperature is, kinetic energy is, and potential energy is constant. All right? Should be a piece of cake, folks. You will have to do this or be able to answer questions about this on your test. What I want you guys to do right now is that page in your packet. Josh, what page are you on right there? Page 8. All right, I want you to go back and re-answer those questions, see if you need to make any changes to what you did the other day. So, some practice, guys. These are typical type of questions you're going to have to answer, all right, on your test or on your final. So it says, what is the freezing point? First off, what type of curve do we have going on here? We've got a heating curve, so it might be helpful for you to kind of draw your lines to help you answer some questions. We've got solid here, solid to liquid here. We've got liquid, liquid to gas, and then we've got our gas phase right there. Some basic things. Freezing point, guys. Freezing, what does freezing mean? No, it does not mean absolute zero. It means what, Brent? It's going from a liquid to a solid. Now, do we see anywhere on this graph where we go from a liquid to a solid? No, because freezing implies what type of energy loss or gain? Is it loss or gain? Loss, right? Freezing is where you're losing energy. You're going from a faster moving particle, which is the liquid state, to the solid state where they're moving slower, so you're losing energy. Our graph does not show that, right? Right? But what if, guys, we flipped it around in our minds, because it's still dealing with a solid and liquid state. So freezing would just be the absence or the removal of heat, even though our graph is showing the addition of heat here because it's a heating curve. The freezing point is still going to be at the same temperature as our what point that this shows? Melting point, guys, because melting is going from solid to liquid. Freezing is going from the liquid to the solid. It's still the same temperature point. What temperature is the melting point at? 5 degrees Celsius. So that's question number 3, but it's going to be the same as the first question as well. They're both at the same temperature. One is the addition of heat, one is the removal of heat. All right? You've got to be able to recognize that. Think about the states of matter that are involved with both of those processes. Boiling point. Boiling means what? Liquid to gas. Does our graph show that? Absolutely. So what temperature would that be? Is this substance we're looking at water? No. How do we know that?
Doesn't boil at
Doesn't boil at what? What temperature, guys, does water boil at? 100 degrees Celsius. We don't use Fahrenheit in this class. What temperature does it freeze or melt at? 0 degrees Celsius, right? So obviously, guys, we should be able to know that, hey, it's not water. That's the only substance that we know about that we can rule out. It could be something else. It is something else. What letter represents the range where the solid is being warmed? Liquid being warmed. Vapor being warmed. All right. What letter represents the melting of the solid? Vaporization of the liquid. What letter shows a change in potential energy? Potential means what? Not moving, guys. Think about this. Flat equals phase change, which equals potential energy change. Flat phase potential. So, what letter or letters is potential at? B and D. What about kinetic change? What letter represents condensation? Does our graph show condensation? No, so condensation is the opposite of what phase change? Boiling or vaporization. So condensation point is going to be D. And then what represents solidification? B. What's another term for solidification? Freezing or fusion. All right, melting is the opposite of it. Melting is the opposite. Folks, these are the types of questions you're going to have to answer. My hope is that they're easy questions, especially now that we've gone through it. You may have been confused the other day. My hope is that you're not confused anymore. All right? All right, the next thing we're going to talk about in our foldable are phase diagrams. Phase diagrams. So flip to this page right here. So our phase diagrams, guys, they show the relationship between pressure and temperature. Those are our the axes that we have there. So you've got to be able to know which section of the graph shows which state of matter. Easiest way to remember that is to kind of go around the horn. All right, I start over here. I go solid, liquid, gas. All right, solid, liquid, and gas. It's always going to be that order no matter what the lines look like. Solid, liquid, and gas in that order. So now we've got a couple different points here that you were supposed to look at and identify and label. One of them being this one right here in the center. What is that one called? That's our triple point, which means what? Right. You've got all the states of matter. Okay, you got all the states of matter present at the exact same time. All right. Up here, this is another point at the end of the liquid and gas line. What is that called? The what? What'd you say, Noah? Not the boiling point. A lot of people think that. It's the critical point. All right, it's the critical point. Guys, that means after that point, the substance can no longer exist as a what? It cannot exist as anything but a gas. So after that point, it's always a gas. All right? So you can kind of draw a line kind of going up. It's a gas past that point. Solids, guys, what you want to remember with solids, all right, they have a higher pressure and a lower temperature. That should make sense, right? Because those particles are going to be densely packed together, and they're not going to be moving as much. Lower temperature means they're not moving as much. Higher pressure means they're closer together. Liquids are going to have a higher pressure and a higher temperature. So they are close together, not as close together as solids, but they're also moving a lot more. That's where they get that higher temperature. And then gases are going to have the lower pressure and higher temperature, right? Those are our ideal conditions. Faster the temperature, lower the pressure, the more they can move apart, the faster they can move. Okay? Now, as we go up, guys, here, we're increasing pressure. As we go further to the right, we are increasing the temperature. The other thing that you've got to be able to do with these phase diagrams is not only know where the states of matter are and kind of what's going on with their pressure and temperature, but as we go across the lines here, they represent phase changes, right? Because you're going from one thing to another. So we're going to start up here at the top. As I go from left to right across this line, I'm going from a solid state to a liquid state. What is that called? as we go from solid to liquid, guys, this is our melting phase change. All right. The opposite of that, if we go back from the liquid to solid, is called what? Fusion or solidification or freezing. All of those mean the same thing. All right? All of those mean the same thing. Now, if we go down here to the bottom, as we go from a solid directly to the gas, what is that known as? That is sublimation. When we go from the gas back to the solid, that is known as deposition. That's probably a new term. All right, before this unit. All right, before we start this, is probably the newest term for you guys. And then over here, we go from the liquid to the gas is known as, what is it? Not evaporation, vaporization or so as we go back from gas back to a liquid, what is that called? Condensation. All right, condensation. Now there's one other thing, guys, I want us to add to this table, to this graph. I'm going to do it in a different color. I'm going to do it in red. All right. I'm going to add dotted lines. I'm going to add a dotted line. All right. What this dotted line represents, guys, is I'm going to say this is a specific pressure. This is 1 atmosphere. Okay, 1 atmosphere. That should mean something to you. 1 atmosphere in your reading is known as what? Standard pressure, right? It's 1 atmosphere, 760 torr, 760 millimeters mercury, 101.3 kPa. All right, that's our standard pressure, guys. That also means another thing. Not only is it standard pressure, there's another term that means the same thing. That's called normal pressure. Normal pressure, guys, are normal. So if you're asked about the normal boiling point or normal melting point or something like that, it's the point at 1 atm or 760 torr and all that other stuff there. All right. So right here, this dot would be our normal what? Normal melting / freezing point. Okay, that's our normal melting and freezing point. This second red dot is going to be my what? Normal boiling / condensation point. All right. Normal means atmospheric pressure, guys. Standard pressure. All right, that term normal. And you will see that not only on your test next week, but your final exam. You've got to know what it means when it says what's the normal boiling point or normal melting point. What I want you guys to do right now is to go back and re-look at your questions on page, Page 10. Page 10. All right, so what section represents the solid phase? A. Liquid phase? Gas? Okay. Triple point? D. Critical point? Yeah, that's that. Whatever. You can call it E or theta, guys. All right, I'm going to call it E. What is the substance's normal melting point?
60 degrees.
All right, so why is it 60? Because, again, you go to 1 atm. Our pressure, guys, is atmospheres. All right, so we're going to go over here, down, 60 degrees Celsius. Boiling point, normal boiling point? 100 degrees Celsius. Above what temperature is it impossible to liquefy the substance no matter what the pressure is? 110, guys, that's your critical point. At what temperature and pressure do all three phases coexist? What point is that? Right, that's your triple point, and that's going to be 45 degrees and 0.5 atm. Is the density of the solid greater than or less than the liquid? We'll talk about that tomorrow. Would an increase in pressure cause the substance to freeze or melt? We will talk about these last two, guys, tomorrow.